Organizers, Anne and Sebastiano and Hakim and Pierre, for this invitation to come and talk in 200 kilometers away from Saas-Fee. For those that don't know me, my name is Matt Hayes. I am from the Stockholm University Department of Astronomy and the Oscar Klein Center for Cosmoparticle Physics. Cosmoparticle is a word that we made up for the new center. But okay, so when I received an email to come and to speak here, an invitation, almost 18 months ago, it said I would be asked to come and talk about observations of Lyman-alpha transfer in the local universe. And I agreed and I said yes and I signed the contract. And then about a year after this, or 6 months ago, I realized this doesn't make any sense, right? You can't observe the Lyman-alpha transfer itself. So I sent an email to the organizers and it was, well, I didn't get a reply anyway, so I've taken it upon myself to change the title to Observations, Lyman-alpha, something, galaxies in the local universe. Everything else is going to be the same, all right? So it's just the title. So this is an overview of what I'm going to spend the next, well, not the next, but 6 hours over the rest of this week talking about. The breakdown is that today, for the rest of this hour, I'm going to present what I'm calling key concepts, some of the basic astrophysics, what I've called prerequisites, the kind of things that you need to really understand Lyman-alpha observations. It's not unique to the low redshift universe. It's kind of, in some senses, more relevant in the low redshift universe, because this is a redshift where we can go and get all the information we want, measure all the properties of galaxies that we want, almost. Tomorrow I'm going to talk about some of the relevant history. I think it's very important to know where we come from. This is the first UV observations, or the first vacuum UV observations, taken from sounding rockets, taken from satellites, concerning the first AGN spectra and starbursts. And then I have 3 lectures that I've dedicated to surveys of the local universe. This is going to be broad Lyman-alpha spectrophotometry and surveys in lecture 3. And then in lectures 4 and 5, I'm going to talk in more detail about observations that we do with the Hubble Space Telescope. So higher resolution spectroscopy, higher resolution imaging, where we can really start to understand the properties of the ISM and the star-forming regions. And then in the last hour, hopefully, if everything goes well, then I'll try and draw everything together into some kind of conclusive whole and summarize what we know, how we understand about how Lyman-alpha escapes, what we would like to answer in the future, and hopefully have some discussion as well. I'd like you to keep in mind, actually, over the course of these lectures. Okay, so Masami's talking about the high redshift universe and galaxy surveys, and keep in mind that all this data going back 20 years, they come from telescopes. You know, we have on the ground, we have four VLTs, we have 2 Kecks, we have 2 Geminis, we have MMT and Magellan and the Het and the SALT, and I don't know, in excess of 10 8-meter class telescopes. We have the same, more 4-meter class telescopes, and the first Lyman-alpha emitters were actually detected on 2 meters. We have all of these telescopes still. We have one observatory that we can do Lyman-alpha in the local universe with. And that's the Hubble Space Telescope. And a lot of these observations come from there. But also keep in mind that this is a telescope. It has 1 annual proposal cycle. The deadline for that is 3 weeks and 4 days from now. And that if you want to be working in this kind of field or to do anything in this field, that's your deadline. Also, keep in mind, of course, that unlike the ground-based telescopes, this is not something that we can fix anymore. And any single point failure with the observatory is going to end ultraviolet astronomy. And that could happen any time. So this year is probably better than next year. So that sounds quite negative, doesn't it? But all right, let's go on. I mean, it's supposed to, it's my version of inspiring, right? Okay, so I'm going to talk, observations of the local universe. How this slide gets in here again. That's the Yeah, I'm talking about key concepts of verbal definitions and methods. Yeah, I'd like to acknowledge from the archive admin significant content overlap with Mark Dijkstra and Masami Uchi, to a lesser extent Xavier Prochaska. Here I will present reasons why we do this kind of thing, some of the basic astrophysics, some calculations that overlap a little bit with Mark, but in a different way. What you actually need to observe Lyman-alpha in the low redshift universe, where you need to be, what kind of facilities you need, and I intend to end with a summary of what available tools we have and what their capabilities are. So, motivations and background, I can rewrite as why would one do such a thing. Attempt to observe Lyman-alpha in the local universe when, we already have above 1,000 spectra samples, photometric samples of 10,000 galaxies. But beyond redshift of 2, why we would waste so much money working with expensive space observatories? Well, right now, as Masami has pointed out, we have at least 10 to the 3 Lyman-alpha spectra and probably several thousand more sitting in archives. We know a lot about the Lyman-alpha output from Lyman break galaxies. We know this is the current state of play, few 10 to the 3 spectra. But by the end of this decade, this is going to reach what I'm calling, industrial scale. There's going to be 1 million Lyman-alpha spectra in the archives, right? We will have 1 million Lyman-alpha spectra. Now, as I had hoped Mark would have derived by now and hasn't quite got to, of all the ionizing photons produced by all the massive stars in the universe, they all, or the vast majority of them, get absorbed in astrophysical nebulae, ionized hydrogen. And 68% of these ionizing photons, they all get reprocessed through the Lyman-alpha channel. So, for 2/3 of all ionizing photons end up making Lyman-alpha. This is the Rydberg formula that Mark has already introduced. You have, the energy, or the inverse of the wavelength, going as some constant, and then in brackets you have the inverse subtraction of the squares of the n of the lower and upper energy levels, where n is this principal quantum number. If you insert a 1 and a 2 in there, you get 1 minus 1/4, so the energy of a Lyman-alpha photon is precisely 3/4 of 1 Rydberg for the n to 2, n equals 2 to 1 transition. And this is precisely 3/4 the energy at the ionization edge. So if you assume that all ionizing photons have a energy of 13.6 eV, so then they all have energies just below the ionization edge, then roughly half of the ionizing energy of all massive stars is going to be reprocessed in just one narrow emission line with plus or minus 1 angstrom in full width half maximum. It's going to be extremely bright. If you adopt sort of typical star formation rate calibrations for H alpha scaled by the intrinsic line ratio, and I take, for example, a galaxy that has a star formation rate of 5 solar masses per year, and I convert that to a Lyman-alpha flux, and I assume Lyman-alpha luminosity, and I assume an escape fraction of 1 and a redshift of 6, and say that I want a signal-to-noise ratio of 7, then from an 8-meter telescope in Chile, you can do that in less than 1 hour. This is one of the reasons why Lyman-alpha is so very important. And this is the reason why we build these telescopes, right? Because it carries away so much energy, intrinsically. It also has a very high intrinsic equivalent width. So for constant star formation rates, we're talking equivalent widths of about 100 angstroms. So it's high contrast in comparison to the continuum. It isn't just luminous. It's also very easy, technically, to observe. It's visible to ground-based telescopes between redshifts of 2 and 7. And this is, of course, why we're going out and getting enormous samples of Lyman-alpha emitters. These are the facilities that are coming online, are online. We have MUSE, we have HyperSupremeCam. MUSE is at VLT, HyperSupremeCam's on at the Subaru telescope, HET-DEC's coming on at Hobby Eberly, Cosmic Web Imagers at Palomar, and then at the Keck. That's right, Keck this year? Okay, yeah. Keck now, right? And then, of course, not very far in the future, we have extremely large telescopes. These machines are motivated in part or in whole by the detection of Lyman-alpha in the early universe. And at the beyond redshift of 2 or so, Galaxies are a very, very, very long way away, and what you end up with measurements of is the flux. If you integrate the spectral line profile, if you divide that by the continuum level, you get an equivalent width. You can probably measure full width half maximum, and you can maybe, if you're lucky, you have the right resolution and the right signal to noise, you can start to measure the line profiles. These may look p-Cygni-like, asymmetric. You may end up with asymmetric lines either from transfer in the interstellar medium or intergalactic medium. Or you end up with double peaks. You can infer things about the column density and the kinematics of these galaxies. But unless you know fundamentally under the surface what the intrinsic luminosity, what the intrinsic line profile is, you have no way of calibrating these things, no way of fully understanding what you're seeing. So the goals of this science, and reasons why we work at low redshift, is we'd like to understand precisely how you read information off the Lyman-alpha profile, how you infer information from the escape fraction, how this is, of course, evolving with redshift, and what that means for galaxy evolution. And to get these observations to really do these calibrations, it's not something you will be able to do regardless of how many high-Z Lyman-alpha observations you have, right? It's low redshift universe science. So Lyman-alpha is very important. I think that's kind of clear, but it's also optically thick, right? Emission can be subject to a large, large number of physical properties that you don't know for the average galaxy. Lyman-alpha is in the far ultraviolet, right? This is where dust attenuation curves peak. For the Calzetti law, the extinction coefficient at Lyman-alpha is about 12, which gives you a fractional output, or I over I0, of about 0.1, 10% for very modest reddenings of 0.2 in EB minus V. That's before you consider things like resonance scattering, which is going to increase the path Lyman-alpha takes, decrease the throughput, or decrease the amount of Lyman-alpha that gets out. Lyman-alpha becomes optically thick according to, the optical depth goes to this expression here. You have a number that's 10 to the minus 13, and a temperature, and a column density, and a Voigt profile. All these numbers very close to 1, so you see that Lyman-alpha becomes optically thick at about 10 to the minus 14 atoms per cc. Sorry, atoms per square centimeter. That's basically all galaxies. And this H1 can take any distribution of kinematics and spatial distribution and clumping it wants. This is a diagram from one of Anne Veram's papers. It's the one that we always bring out in conference talks to indicate how complicated Lyman-alpha radiation transfer is. You see, you can have multiple bumps here, various peaks as a function of frequency, 1, 2, 3, 4, depending on the properties of the ISM. This is just done by taking a radiation source, Lyman-alpha photons, inside a spherical shell of hydrogen that includes some dust. You can make this shell move as fast as you want, or change the column density of dust or gas. And you can get out a wide, wide variety of line profiles with a wide, wide variety of escape fractions. And that's for the simplest perfect geometry of a bubble with a single velocity. Of course, in the low redshift universe, you can actually go and observe atomic hydrogen in galaxies using the 21 centimeter line and interferometers. And we see that galaxies don't tend to look like bubbles. These are observations from the THINGS survey combined with galaxy UV photometry. And the pinky colors in the middle, those are massive stars, UV bright. This is where the ionizing radiation is produced. This is where Lyman-alpha is produced. And in the blue, stuff that you don't see very well under this light, but you see that this is the H1 in the light blue colors. It's clumpy, it has holes in it. Clearly Lyman-alpha is going to prefer to go some ways and not others. I mean, here you have all kinds of shells with big lumpy holes in the middle of them. You could very well envisage that Lyman-alpha would look very different depending on how you view any of these galaxies, and also where precisely and how you inject Lyman-alpha radiation. So calibrations that one may want to apply to high redshift galaxies, you might want to know things like star formation rate, you might want to know things like dust attenuation, the metallicity, and the ISM mass, and there are many calibrations for these derived in the local universe, also using lots of models, but all the observations they're calibrated against are all done here, either in the galaxy or in nearby galaxies. Okay, there's nothing, well, almost no calibrations or correlations between physically derived properties and observables actually done at high redshift. It's almost ubiquitously applying things out of the box, calibrated very nearby. So you would imagine, for example, that you want to observe H alpha. Well, H alpha you can do in some metal lines out to redshift 2.5, 3.5 if you include H beta in the strong O3 lines. It's possible. It's very, very challenging. Dust continuum is of course possible in the 850 micron window. What you see there is not the median Lyman-alpha emitter. It's very bright, dusty galaxies. The typical Lyman break galaxy is not detected. It's not bright enough in the far infrared. You want to see, for example, to get stellar mass, something like this, you're best off looking in the K-band at cool stars. This is in the local rest frame, of course. Doing this at high redshift is very, very challenging as well. You need very deep Spitzer observations. Possible, but again, the median Lyman-alpha emitter is not going to be detected. Most importantly of all, I would argue, is actually understanding the H1 without using bright background sources or without using down-the-barrel absorption techniques. So you want to go to 21 centimeter observations to really figure out how much H1 there is in a system, to figure out how much what its distribution is, and also how it's, the motions of the H1 are best done on large scales by interferometry. This is not just around the corner for the high redshift universe. The current record for an individual galaxy detection at H1 21 centimeter is redshift 0.4. People say the SKA is going to be a magic bullet for this kind of science, and the SKA is really going to revolutionize very many areas of astronomy. But in terms of sensitivity, the improvement's significant, right? It's 6 times more sensitive than the VLA currently is. So extending 21 centimeter observations directly to redshift 3 for the average galaxy is still going to result in a non-detection. We're going to argue, probably me and others later on this week, the kinematics is important for Lyman-alpha emission. You're going to want to know how much energy there is in the wind, how much wind is moving, how fast, how much energy is in there. And that's best traced by going to the X-ray. And again, X-ray observations, even at redshift 0.1 for individual starbursts, are very, very challenging. Even with the extremely deep Chandra observations in the CDF South and stacking large samples of Lyman break galaxies, you end up with a non-detection, unless you include the AGN. So the stuff we can do at the low redshift universe is a summary of all the telescopes we use, where we can make detections, right? We're mainly driven by the Hubble Space Telescope nowadays, but we can also use Chandra and XMM if we want to look in the X-ray. Going around, we had the GALEX, GTC and Sloan, and we've, for our projects, have been using NOT and the Calar Alto and the CFHT. So use Spitzer, and because our galaxies are nearby, they're detected by WISE, and you can see them with Herschel, and you can see them with Sophia even. And if you want to look at CO, you can go to IRAM and the NRO and other radio telescopes to look at 21 centimeter. If we look at galaxies below redshift of 0.1, typically we can see them with the GBT, and we can get moderate resolution H1 observations with interferometers. Of course, we're also subject to things like cosmological surface brightness dimming, right? Surface brightness, everybody knows, it's going to be is independent of distance, right? It doesn't matter how far away you move something, its surface brightness remained unchanged. It's only affected by cosmology. So in the continuum, surface brightness declines cosmologically as 1 plus z to the 4th power. And when you integrate over one dimension of wavelength, this declines to 1 plus e to the 3rd power only. So in the galaxies that Masami is talking about beyond redshift of 2, you insert a 2 in here, and you get 3 to the 3rd power. You get a factor of 27 in cosmological surface brightness dimming at the lowest redshift at which you can do Lyman-alpha from the ground. When you look at redshift 4, this becomes 125 and 500 by redshift 7, close to the current record, right? Factor of 500 lost in cosmological surface brightness dimming. And if you want to look in the continuum, it's 1 plus z worse. It's 4,000. When we look at redshift below, say, 0.1, you can put a 0.1 in this equation here, and you can have 1.1 to the power of 3. So we lose a factor of almost nothing in cosmological surface brightness dimming. This next slide is really, really obvious, right? The further away you move something, the smaller it's going to look. But, you know, this side of redshift 0.1, we have redshift on x and angular scale on y. You can see things with 1 arcsecond resolution down to scales of about 1 kiloparsec. This side of redshift 0.1. It's going to become about 8 kiloparsecs at redshift 2. But we can do Lyman-alpha down to almost a little bit this side of redshift 0.01, which means we can resolve scales of 100 parsecs from the ground. Of course, you can't see Lyman-alpha from the ground, and you need an HST. And then, you know, the point spread function goes down by another order of magnitude, and we can see scales down to 40 parsecs for the nearest galaxies. This is, of course, what high redshift galaxies look like. Don't see very much detail. This is what galaxies in the local universe look like, some starbursts. You see a lot of detail. This is an example of Lyman-alpha imaging that we do with HST. What you're seeing here in green is massive stars, bright UV radiation taken by taken by a UV continuum filter in the ACS of HST. The green bits are where ionizing photons are produced. The star clusters are really the only environments in which you form most stars, probably. It's where they make the ionizing photons. Ionizing photons travel not very far before they ionize, and they make a nebula. That you usually trace most easily by using narrowband filters at H-alpha. That's what we see in red here. So when you see green spots are usually embedded in red lumps, which shows us that the ionizing photons travel a certain way before they ionize the ISM. And green spots have some H-alpha emission around them. And these red regions here, where we see H-alpha, these are the recombination nebulae in which Lyman-alpha is being produced. Has to be, set by quantum mechanics. But the blue light in this image is how the Lyman-alpha emission looks. And we see in these examples, well, this example, that Lyman-alpha seems to want to have nothing to do with the regions in which it's produced. It wants to come out from basically anywhere else, and it comes out in fars, top and bottom over here. There's spots around, maybe beginnings associated with star clusters. But broadly speaking, you can say it's completely decoupled. When you look at Lyman-alpha with a spectrograph, of course, you can collect many photons. But particularly with new spectrographs on HST, in one shot you get several hundred angstroms that include many features from stellar winds. This is just a spectrum of a stack of 800 Lyman break galaxies to illustrate all the features, because it's actually quite a nice stack with many details in it. But we see features of things like nitrogen-5 and silicon-4 that form in the outflows of massive stars. We can trace atomic gas by using absorption lines of H1 if we like things like H-beta, but also other metal ions that form in the same medium. Silicon-2, oxygen-1, carbon-2, things like this. H1 observation, the H2 regions from Lyman-alpha and helium-2 if we're lucky, and carbon-3. Hotter interstellar lines like silicon-3 and 4, and we also get the UV continuum shape. All this information free in our spectra, and this tells us about the ages and metallicities of stars, abundances, how thick the gas column is, tells us about how much dust there is, what the covering fractions are, all the extinction. Tells us, a great deal of information about the stars and the gas that surrounds them, and this is relatively straightforward. And the final motivator is this. This is the front page of the course, and this is the little banner figure here. And if you go to the directory in which these images are stored, you list it here, and all of the images but 2 are taken at low redshift. So it must be really, really important. So just to recapitulate a little bit, we have all of these fantastic instruments that are either here or just around the corner. We're on the brink of a revolution in Lyman-alpha science, in the high redshift universe, and in the vacuum UV, we are very close to the end of an era. So the basic elements of Lyman-alpha production Okay, this diagram's been up in at least 2 talks already today. It's from this Partridge and Peebles paper, 1967. It's written in frequency here, so this is the blue end and this is the red end. And I have drawn a triangle on my diagram, and that's to illustrate the integral of all the ionizing photons that have been absorbed by H1. This, of course, introduces the continuum break that we actually know as the Lyman break. That makes nebulae. We have a recombination cascade. You make Lyman-alpha down here. That imprints this line on the spectrum. I'm not quite sure why this slide is in this part of the spectrum. But okay, to cover some... Oh yeah, it was because of this. This is the abstract of a classic paper from 1993 by Charlot and Fall. So it's about Lyman-alpha emission from galaxies. You might notice that the lead author is Stéphane Charlot, and the year was 1993, when computerized population synthesis was becoming particularly important, and Stéphane Charlot was one of the real pioneers of this field, and he made some diagrams that look like this, right? Synthetic spectra produced by stellar libraries that evolve with time to predict the spectra of galaxies. You have wavelength on the x-axis and frequency on the y. No, you don't. Wavelength on the x-axis and what did I say? Flux, that's the word, on the y-axis in log. This is for a starburst spectrum at ages of 10 to the 7, 10 to the 8 years, and you see that between very early times at 10 mega years, you have a UV continuum, which is very blue, quite bright. You produce a lot of non-ionizing UV, and you also produce a lot of ionizing UV. And then when you let this system evolve by 100 million years, you lose about an order of magnitude in the non-ionizing UV, but you lose 3 orders of magnitude here, or even more, at ionizing wavelengths. So for every 1,000 ionizing photons you had, you now have 1. And so this shows you that if you want to make a Lyman-alpha line, which is just reprocessing ionizing radiation, you better have some O-stars around. You have to have a very young population, and since they're so short-lived, you're going to have to be making them basically now. If you change the star formation history to one that's constant, so the star formation rate is just proceeding at the same rate with time, now the ionizing continuum is a constant. It doesn't matter how old the system is, because O-stars are so short-lived that this just converges into a constant value. And the non-ionizing UV takes a little time to ramp up and becomes constant after 100 or 200 mega years. What this means for the equivalent width with time is that at early times for a burst and for a salpeter IMF here, you have equivalent widths of around 240 angstroms, so very bright, very high contrast with the continuum. And for a constant star formation rate, this converges for a salpeter or close to salpeter IMF at 80 angstroms. And these numbers are quite commonly pulled out in papers, and this is the paper in which they were first derived. This is an extension of that done by Daniel Scherer using population 3-star models. Here you really do overproduce the ionizing output of stars compared to the non-ionizing. And you can really, at very, very young, very, very early times, really drive the Lyman-alpha equivalent width up to 1,000 angstroms. So if we want to know how much Lyman-alpha is intrinsically produced, and we don't have an observation of Lyman-alpha, and even if we do have an observation of Lyman-alpha, we don't know how much is going to be escaping, we want to know how to estimate the intrinsic Lyman-alpha flux, right? This requires an observation of another emission line, something like H-alpha that's going to form in exactly the same places as Lyman-alpha. So this is a calculation that I did on the flight yesterday. This is a grid of Lyman-alpha to H-alpha ratios running between about 8 in this dark blue and 13 in red for electron densities running between 1 per cc and a million, between 1,000 Kelvin and 30,000 Kelvin. And for the most part of this figure, or if you look between basically any temperature, between 100 and 10 to the 4 degrees, you're really not doing anything to this ratio between it being about 8 and 10, right? So Lyman-alpha over H-alpha takes a value between 8 and 10, more or less regardless of the electron density and the temperature. It's very useful in computing the, the intrinsic Lyman-alpha flux. Just for fun, I ran this up to also very high densities, and the thing starts going backwards. It's because you start draining out the, when you start to decrease the Lyman-alpha H-alpha ratio when you work at very high densities. You have a lot of free electrons around that actually do collisionally exchange electrons between this 2p and 2s level that we were discussing earlier on, and you start to drain Lyman-alpha to the 2-photon channel. So if you want to estimate intrinsic Lyman-alpha, you might want to go to H-alpha. H-alpha is very strong at 1/10 Lyman-alpha. It's pretty respectable. However you observe, it's probably going to have kind of similar spatial resolution. It's moderately optically thin in that it reaches tau of 1 at EB minus V of 0.3 for Calzetti dust, which is, I mean, you still get, that's kind of dusty, and you're still getting more than half of your H-alpha photons out, so, well, no, more than a third of your H-alpha photons out. So, you know, it's not bad. You can see it from the ground at redshift 2. H-beta would be visible also from the ground in principle to redshift 3.5 or something. Also similar kind of spatial resolution, you'll observe it in the same way. It's much weaker than Lyman-alpha at 1/30th the intrinsic line strength approximately. What you really need to get the intrinsic H-alpha and then the intrinsic Lyman-alpha is of course a combination of the two. You use the H-beta line to dust correct H-alpha for of course, you need to do this, you need to get both emission lines and detect them both. And also one has to keep in mind that you're only correcting the light you can see. So in star-forming galaxies, typically you have some regions that are reasonably optically thin and some very, very thick, very, very dusty, dense regions. And these emit almost none of their H-alpha radiation whatsoever. And in that limit, it doesn't matter if you have H-beta. You just, you can only dust correct light down to a few optical depths. And if it's something's buried behind 10 magnitudes of extinction, it doesn't matter what observations you have in H-beta. It'd be preferable, of course, to go to more optically thin radiation, like the Paschen and bracket series in the near infrared. You can do bracket out to bracket gamma. It's very nice. Doesn't become optically thick until EB minus V of a few. But these lines are also very weak, up to 1,000th the strength of Lyman-alpha. So, you have to fight against a bright near-infrared sky background. And somewhat curiously, no one has published, for example, Paschen beta or bracket gamma observations of local starburst galaxies that have Lyman-alpha observations. I would encourage somebody to do that. People say that the radio recombination lines are also some kind of gold standard for getting at the intrinsic Lyman-alpha flux. Things like H44 alpha to H66 alpha that you can see with ALMA and with the VLA. These lines will in principle, well, they're completely optically thin. Dust will not affect the line at all. Where are we? Of course, you need to go to radio interferometers. That's better at high frequency to get more spatial resolution, but then you have to rely on the atmosphere behaving itself. But more importantly, nobody has done this yet. There's very few radio recombination line observations of starburst galaxies and none where Lyman-alpha observations exist. So this morning, Xavier Prochaska mentioned that the branching ratio, or not even, that the calibration of these radio recombination lines is, there's an intrinsic uncertainty to what you know about the energy levels based upon the uncertainty principle. And that applies, of course, to the Lyman-alpha transition, where it's basically negligible at 1 part in 10 to the 8, I think it was. That same quantum mechanical uncertainty applies also to radio recombination lines, where it amounts to a factor of a few. So whatever you do with these lines, you can certainly get to the intrinsic morphology of the nebulae and the intrinsic line profile in velocity space, but it will tell you the intrinsic ionization rate to no better than a factor of a few. And then you can have also many other calibrations of star formation rate, UV, SED fitting, dust, bolometric luminosities in the far infrared. But these, of course, will have different star formation timescales to emission lines, and they're based on, you have different equilibrium and heating of the dust. What is important, what is really good, is that the extinction law in getting at the intrinsic Lyman-alpha profile is basically irrelevant. So it doesn't matter what the dust composition is, it doesn't matter what law you adopt. If you have H beta anything bluer than H beta, the extinction coefficients for any extinction law are basically identical. So getting at the intrinsic Balmer line radiation, Balmer strength is, provided you get the two lines, then you can do it. There is no dependence on the extinction law here. Regardless of the law, regardless of the normalization or the RV. Laws change dramatically in the UV, it's absolutely true. But as we said, you know, to compute the intrinsic Lyman-alpha, all you need to have is an intrinsic Balmer line. So this is some points about definitions. Of course, Lyman-alpha is a complicated line to work with. It's a complicated line to measure. The estimate of a flux in an emission line requires you to account from the continuum, right? You have an observation like this with a bright Lyman-alpha line, and you see a continuum down there. You have to subtract that, and in this case, that looks pretty straightforward. You would just fit some kind of line that goes across there. And you would subtract it, and then you can either fit a profile to that or numerically integrate the line, and then you're done. Unfortunately, there are some more complications than that. If you want to look at this strong absorption line here, for example, here you do see the Lorentzian absorption wings that were being discussed this morning. And if you want to measure the continuum here, well, you have to be absolutely certain that you're doing it reasonably so far away from the line center that these absorption wings don't matter. Of course, if you measure down here where the absorption wings truly don't matter, the color of the continuum starts to become important. And this is a consideration that you might want to at least keep in mind. So Lyman-alpha can also take these P Cygni line profiles where you have a continuum here, an emission line which is asymmetric, and an absorption line, and it's a matter of definition about what you call the Lyman-alpha flux from this system. You might say, if you would say want to look at the nebular line strength, you'd want to integrate just this here, or if you want to take the total flux that you would measure by, say, narrowband imaging, it's going to certainly include the absorption part as well. Here, the absorption equivalent width from the interstellar medium can go up to something like 50 angstroms in equivalent width. So if you have a very thick ISM and 80 angstroms equivalent width in emission, which is what you get for constant star formation, it's almost going to eat the whole thing. So you also have to do something to the ISM to make sure you don't get this very thick absorption. And your ability to separate between emission and absorption here, if you do care about only the emission part, is going to be strongly dependent on your spectral resolution. High resolution you can do it. With narrowband imaging you certainly can't. Everybody's paying attention. There are the part twos. There's also stellar absorption, which is also neglected, but it's worth at least keeping in mind, right, that Lyman-alpha radiation transfer in stars is going to be no different from Lyman-alpha radiation transfer in galaxies. There's going to be some MH1 around depending on the temperature of the star, and that's going to scatter and absorb Lyman-alpha photons. So I just ran some very simple Starburst 99 simulations, also on flight yesterday, just plotting the Lyman-alpha line profile as a function of age for an instantaneous burst. And here at 1 megayear, okay, there's 1216 about there, I see there's a feature there. I think that's actually nitrogen 5, not Lyman-alpha. But here at Lyman-alpha, there is, okay, we're safe there. There's not an absorption feature. 5 megayears, there's an absorption feature, and you haven't lost many supernovae in 5 megayears. So the temperature of the stars that dominates the stellar population has not changed very much. 10 megayears changed a lot. There you see there's a prominent Lyman-alpha line in absorption, and as you go to 30, 100 megayears, indeed, there's a strong line. Now, if you just look at this, zoom in a little bit, you can see the line here. There's 1216. You can see the line out to, well, at least 230 angstroms. And this can do plus or minus 30 angstroms, which can amount to an equivalent width and absorption of about 40 angstroms. So if we say that you can get 80 angstroms in emission for continuous star formation, it could be significant depending on what dominates the stellar population. This is just some plots of using stellar atmosphere models and also some observations about what kind of absorption equivalent widths you expect from stellar populations with stars dominated by this temperature. So here at about, you're quite good, 10 to the 30,000 Kelvin, just a couple of angstroms in absorption. But once you go below sort of 15,000 Kelvin, you're up here at 30 angstroms in equivalent width being absorbed by stars. These are just the same diagram plotted the other way using more recent simulations. Now, I hope now that a good fraction of you are saying, well, you know, O stars for bursts with 30 megayears, that's not something that can happen. And that's right, you know, you have lost all your ionizing stars by that point. But the age is, I mean, there's no such thing as an age when you don't have a star formation history. And a significant fraction of Lyman-alpha emitters are red. This was quite a fashionable thing to say 10 years ago. I'm not sure now what the fraction of red Lyman-alpha emitters is, but and if they're red because of dust reddening, then it's fine. Indeed, it doesn't matter. You still can have basically no stellar absorption in very young populations dominating the ionizing continuum. The continuum near Lyman-alpha. But in fact, if some of these galaxies are red because they have old stellar populations with recent bursts on top of them, so here you have a red spectrum, and then Lyman-alpha, a minority of the galaxies forming stars that makes Lyman-alpha. Indeed, you could, in integrated photometry, have decent amount of stellar light, reasonably strong stellar absorption feature. And also, star formation in the UV is particularly clumpy. So this is a map of a star-forming galaxy in 1500 angstroms, and it's, you know, the black spots here are the star-forming clusters where you really have O stars. Of course, there are stars everywhere. I mean, the starbursts tend not to be global, right? There's usually a host in a starburst galaxy. You can have any old population. And if you care about the Lyman-alpha emission from here, fine. Probably there's not going to be any stellar absorption, but out here in these fuzzy regions, it's certainly particularly plausible. So, Sebastian, how long have I got? 2 minutes. I'm not going to get to the end of this then. So we come back here, I guess. This is, so what do you have to do to observe Lyman-alpha in the local universe? This is the best diagram I could find without, the best diagram I could find in the amount of time I spent looking. This is how much light the atmosphere transmits, the function of wavelength. Here you have now down at, you can do what we're calling mid-ultraviolet down here from altitudes of about 40 kilometers. It's about 2,000 angstroms, which you can do on balloons. It's possible to do it on balloons. And then at 2,000 angstroms, that puts your Lyman-alpha line about redshift 1, which is very nice. There's a lot of missing science at redshift of 1 and Lyman-alpha. It'd be very, very good to have some very big samples there. But if you want to do real vacuum UV observations below 1,500 angstroms, take Lyman-alpha in below redshift of 0.4, you have to go to altitudes of beyond 150 kilometers. It has to be done with rockets or satellites. So is it enough just to go to space? Well, unfortunately, it's not enough just to go to space. This is a map of the H1 column density in our galaxy. So you have color-coded, this is in galactic coordinates, and color-coded here is the column density. Here in white is about 10 to the 20 per centimeter square. This red line here is 2 times 10 to the 20 per centimeter square. It's the definition of a damped Lyman-alpha absorber. And that's coming in at light blue color here. And everything darker than that in this figure is a sight line that you would call a DLA. And there's nowhere on that diagram that that's not true. So the Milky Way, almost every direction you look, has a thick enough H1 column to absorb all the Lyman-alpha that would get through if there is no redshift. And moreover, the Milky Way, no. The atmosphere of our star, no. What we call planet, the Earth, geocorona. Geocoronal Lyman-alpha emission is what I'm getting at. There's also recombinations in the upper atmosphere that make Lyman-alpha radiation at a surface brightness that is tens of times brighter than the Lyman-alpha flux you receive from any astrophysical source. There's a very bright geocoronal Lyman-alpha line which will destroy Lyman-alpha signal from anything you observe at redshift 0.000. There's one sort of happy exception to this. This is M33. This is a UV spectrograph called the UVS that flew on Voyager 2. This is an observation with a slit here. You have date here. This is the slit. Date on the 18th of February, 19th, 20th of February. making a raster observation of this galaxy, has a Lyman-alpha flux of 10 to the minus 9 in CGS units. It's by far the brightest Lyman-alpha emitter known. It also has a redshift, spectroscopic Lyman-alpha redshift of minus 0.005, something like this. There's a lot of attention paid in the literature to the redshift record set by Lyman-alpha. This, you have Citrine, Hippeer. These are some Lyman-alpha redshift record as a function of year. The highest, the record out here is at 8.6, I think it was, we discussed this morning. But to be honest, this observation here by Bill Keel from 1998 is the Lyman-alpha redshift record, in my opinion. These ones up here, they're broken every few months. This one has stood since 1998. It's going to stand for a very long time because you have to build a satellite near the Earth. It's not going to do it. You actually have to get away from the geocoronal Lyman-alpha emission and find a good hole in the Milky Way to look through. So maybe that's where I should end. And if I'm going to end there, then I'm going to... Well, I may as well just end there then, right? Now I seem to have broken something. So, okay. That's, yeah. All right. That's all.